This is another important concept in terms of estimations of the volatilities. Very much important in the risk management space again, because the risk keeps changing on a day by day basis. If the risk keeps changing on a day by day basis, how do I compute the today's risk, or how much did the risk change compared to yesterday? That is what is coming out through the estimations of the volatility. Similarly, correlation. Until yesterday, the relationship between Dr. Reddy's and HCL is this much. So today, what could it be? Because this minute aspects play a very important role in your portfolio hedging processes, or even in your trading processes. Because probably you may take that advantage of those minute kind of differences itself today on large volumes, and thus exploiting the differences. Those are some of the things which heavy quant trading oriented companies typically get into. They build models on all these platforms, and based on that they get into the trading processes. So the same, probably will use the same data again for estimating the volatilities using the various mechanisms. We in this chapter we discuss about two mechanisms of estimating the volatility. One is called as an exponential weighted moving average mechanism, EWMA model, and there is one called GARCH model, which uses the definitions which we have covered earlier: auto-regression, conditional heteroscedasticity. Using these two kind of stuff, it actually builds a model to estimate the volatility at each of the periods. Now, if I have to do that, the first assumption that is going there is, the first thing, if I do the estimation of the volatility, what it says is you can do it using the historical data. Using this data, I can estimate the volatility. Probably, as we have done, take the standard deviation of all these days, right? If I take the last 250 days, whatever I have taken as the average of that, the standard deviation of those 250 days is what is my volatility, is my daily volatility, right? And probably if I want the latest volatility, instead of taking the average, see, standard deviation is nothing but the average of the square of the deviation. Variance is nothing but the average of the square of the deviations from the average, and taking the square root of that has given me my standard deviation. So what this mechanism says is, if at all you want to find out for last 20 days or 30 days, for the last 30 days what has been the volatility, right? What it is saying is, let's say I'll not go with the entire data, I'll take the last 30 days, right? For the last 30 days, what is the volatility? I can take the average. If I take the average for the last 30 days, okay, the average returns is to the extent of again 0.001, very close to 0. And the same logic, if I put it to this company, the average return again, even in this case also very close to 0. Now what it says is, the standard deviation is, how am I getting the standard deviations or the variance? I'm subtracting each and every return from this average, doing a square, taking the average. So if I'm taking the last 30 days, what are those last 30 days for me? These are the last 30 days. So probably from this date, right? If I'm considering from this date, the normal model, what I'm doing to estimate the standard deviation, apart from the direct formula, If I'm doing a estimation of the standard deviation, what is that I'm doing? Each and every value, I subtract the average from it and take the square. Each and every value, I subtract the average. This is the way we compute the standard deviation and the variance in our data. First we find out the mean. Each value we subtract the mean, take the square. Okay. Each value I have subtracted the mean. Each value I have subtracted the mean and taken the square. Okay, each value subtracted the mean and taken the square, and I can take the average of those things. The average of those things is what is nothing but my standard deviation or variance. The average of those things is the variance. So what is the variance for me? In this case, the average of these numbers is what is my variance for the Dr. Reddy's, and similarly this is what is the variance for the HCL Tech. Take the square root of these two, I get the daily standard deviation. So the standard deviation, daily standard deviation is 1.8% for this, and it is around 1.72% for this. So if I am looking at it from a standard deviation standpoint, I may say that HCL Tech is slightly less risky compared to Dr. Reddy's or vice versa. Right? Now, how do I estimate this 1.8? Is it forever? Right? From the calculation which we have done, it is for the last 30 days. So can I take the same number for tomorrow? Right? That is where I need an estimation model. Right? So the standard deviation, okay, here it is showing 1.8. Now all I want to know is whether the standard deviation is going up or falling down. What is the pattern in terms of the 30-day standard deviation across the period? And if at all I have to estimate the same, see, probably historically, if you want, you could very well talk about, okay, yesterday's standard deviation means I take it from here up to here, and I say this is the standard deviation as of yesterday for the last 30 days. So historically, if you want, you can easily calculate. But using that knowledge, if I want to do it for the future, right, in the future, when is that the standard deviation is going to go up? When is the standard deviation going to go down? Because there are so many instruments, financial instruments, that get priced based on the standard deviation in the data itself. Right? The options, very heavily they are priced based on the standard deviation. Some option pricing model is there, Black-Scholes model, which actually uses the volatility or sigma as one of the parameters in the formula. Now, what number I should take for sigma? Today if I take, it should be a different sigma. Tomorrow if I take, it should become a different sigma. Only then my estimates become more and more appropriate. Otherwise, it becomes a lot biased in my estimate. If I am using the same sigma for 20 days, that is what a Black-Scholes model even says as one of the assumptions of the model. It assumes that the volatility in the stock is constant for 20 days. Today, it's a very weird assumption to make. Right? Something, the fluctuation is constant. It's not saying there is no fluctuation, but it's saying that fluctuation is constant for a 20-day period. We don't know, right? Today, probably with the recent news floating up, Probably the fluctuations may be much higher in either direction. When the economy is in a very stable state, the fluctuations could be pretty much normal. How can I use one single standard deviation for the entire period? Now, just to give you that thought, let's say I am looking at the standard deviation for this entire year. Instead of last 30 days, if I look at the standard deviation for the entire year, this is saying only 1.3%, whereas this is 1.5%. For the entire year, HCL standard deviation was more compared to Dr. Reddy's, whereas in the last 30 days, Dr. Reddy's standard deviation is more compared to HCL. Now, if I had taken one single number, probably I would have gone with a simple bias that HCL is more riskier than Dr. Reddy's. But if I am looking at the latest trend, latest data, I have to make a conclusion that Dr. Reddy's is more riskier than HCL. Now, the same logic can come into my way for the future also. The order may keep changing. That is where we are bringing in the estimation kind of models, the volatility estimation kind of models. So, these volatility estimation models, what they are coming out with is, now if you see in this entire process, they are asking you to find out the returns. Given the prices, they ask you to find out the returns, especially the continuously compounded kind of return, which is log. Based on the log itself, log today's price by yesterday's price, they ask you to find out the continuously compounded kind of returns. And what they are also suggesting is find out the average returns using that scenario and the standard deviation of the returns. And what it should come out generally, especially if your data size is very small, data frequency is very small, the time periods are very closer, you will see that the mean is very small compared to the standard deviation. And the mean is very close to zero in most of the cases. Especially for this returns kind of scenarios, you will see that the mean for a very small period, it's like for a very minute period, what is the average return? Almost zero, negligible. It will be there, but it will be negligible. From today, see, it's like, okay, from now to another 10 minutes, what is the return? Right, I am investing 100 now. Within another 10 minutes, how much it is going to become? Almost negligible. Probably it may become 100.000001. So it is almost negligible. So that is the first concept it drives with. What it is simply saying is, compute the continuously compounded, we'll do the step by step. Compute the continuously compounded returns, which we have already found out. Compute the mean for last such periods, whether it is 30 or 250, whatever I am doing with, I have computed the mean for those kind of periods. If the period is very small, daily or something, just like the example we have taken, you assume that the mean returns are zero. So, which means though the system has calculated this as the mean, take them as zero. Now, what is the way to compute the variance? Each number minus 0 whole square, which means each number whole squared is what you are doing. Each number minus 0 whole squared, right? Each day's return, what did we do here? Each day's return minus the mean return whole squared. Now we are saying if the time period is very, very small, you assume that the daily return is 0 itself. That's the first assumption these models are going out with. You assume that as 0, which means the variance, what is the way it is coming out? Every value minus 0 whole square, which is nothing but the return squared. Return squared is what is coming out, and the average of the return squared is what we are calling as variance. right? Earlier also we did the same. Each value minus the mean whole squared took the average. That is what we called as variance. Now the only difference we are bringing in this kind of model is take the average as 0, because anyhow they are very minute. They are very close to 0. So you assume them as 0 because we have to derive a model out of it. You assume that to be 0 and recompute the variance, which is nothing but the sum of the return squares. So probably it's as good as saying, now I'll take the return squared. So these are the returns. This is the daily return. I'll take the return squared. These are the return squared, and I'll take the simple average of these return squares. So let's see what are the big differences that they may bring in. Right? Just to bring out a predictability, we are trying out all these scenarios. So I'll take the average of the return squared, which has come out to this much. You see, hardly there is a difference, right? 325, 328. Hardly there is any difference. 347, slightly there is something here. But yeah, in most of the cases, what you will see is the difference literally does not exist. Okay. So this is what is one simple method to find out the variances based on the historical. So what it is saying is the UI squared, which is nothing but the return squared, is contributing to the variance. Very important factor for us. UI squared, which is nothing but the return squared, is contributing to the variance. Now, in this exercise, what we have done, we have taken the average of the last 30 days UI squared. We have taken the average of the last 30 days UI squared and called that as the variance. Now this is where we have given equal weightage to all the 30 days, because average is nothing but simple average. Average of the last 30 days UI squared is nothing but I have given equal weightage to all the 30 days UI squared to arrive at the variance. But in reality, probably for tomorrow, if I have to predict, more weightage should be given to this UI squared than this UI squared. Right? If I have to predict the variance for tomorrow, more weightage should be given to this, probably to this, rather than these, because they are very old. Sometimes they may be because of some specific reason, or over the last 20 days things have changed, things have stabilized. So there is no point. I should not get that much of I should not have the impact of that 20 days back data in the same way for 20 days. Probably it should be a decreasing impact. So weighted average is more necessary instead of a plain simple moving average or simple average for the last 30 days. I can go with a weighted average kind of stuff. So that's where they came up with one practice saying you take alpha I with the UI square. You give some weightage. So probably it's like, okay, you give 5% weightage to this, 4%, 3.5%, 3.2%, 2.5%, whatever it is. You give the weightages in a decreasing way, in such a way that the total weightage is equal to 1. Instead of giving 1 by 30 weightage to all the 30 days, probably you give more than 1 by 30 to the recent, probably 5% or 7% weightage to the latest, and only 0.5% or 0.25% to the 30 days back data, and compute the variance. That's one way they are talking about computation of the variance and using it for the forecasting purpose. One logic. Two, they are also saying, okay, this is a short-term volatility. But we are also saying sometimes the volatility is also a mean reverting factor. See, the risk factor, the fluctuation factor cannot keep going up and up and up and up. Right? Today, if the volatility is very large, it is expected that over a period it has to come down. There is some average level. Okay, the volatility in this particular stock on an average is around 20%. Today, if it is 25 also, slowly it may have to come back to 20. If it is 15 also, it may have to go back to 20. That's a long-term average level. So what it is saying is, now you build a model wherein you predict the volatility for today using this kind of a model. You assume some long-term volatility VL. You assume a long-term volatility VL, or we will build it. You don't need to assume anything. From the data itself, we can extract all these things out. You take a long-term volatility VL, give some weightage to it, gamma, right? And all the short-term UI squares. You take the last 30 days UI squares, give each of them a separate weightage. Give each of them a separate weightage. So what are your total weightages now? Alpha 1 plus alpha 2 plus alpha 3 plus so on alpha n, alpha m plus gamma. These are your total weightages. The total thing should be equal to 1. So which means you may give some 20% weightage to long-term volatility, 80% weightage to short-term volatilities. Out of that 80%, probably 5% to yesterday, 4.5% to day before yesterday. Like that you distribute that 80% across the 30 days. Whatever the volatility that comes up, that is your volatility prediction for each of the days. Now simply speaking, if I have to do that kind, what it says to me is, if at all I am going with a plain average kind of a model, what I'll do for today, if I have to predict, I'll take the average of the last whatever 20 days or 25 days, whatever, right, or 29 days. I'll take the average of those many days. So probably I'm going up with, let's say if I have to do the volatility prediction for today, I'll simply do an addition of these. This is the volatility prediction for today. This is the volatility prediction for today. If it is a plain average basis. Otherwise, I may choose. So what will happen for tomorrow? What is the extra thing that is coming out for tomorrow? The returns. One extra returns are coming up. Right? If I am seeing the last n minus 1. So probably the return squared yesterday whatever was the return squared. Day before yesterday return squared. I am taking the average of all those return squares and saying that that is the variance for today. So for tomorrow what will happen? Probably the 30 days back data is one eliminated and today's return squared is getting added up and the average of that is taken up. So that is what will be the prediction of the average for tomorrow. That is in a plain simple average model. But I may also go with a weighted average. So which means the latest one will get a big weightage and the oldest one. So probably if I just go crudely, I may take the weightages in some form, in a decreasing kind of a format. Right? Probably what I'll do is, one of the crude format that could be applied is, let's say I take the numbers from 1 to, okay, I'll take the weightage as probably 1 divided by the sum of all these. I mean, you don't need to bother about this mechanism, but probably I'll say I'll give a weightage like this. A very old data, I give 0.002 weightage. Very new data, I'll give 0.064 weightage. 6.4% weightage I'll give to the new data, and 0.2% I'll give weightage to the very old data. Now, because of this, what is the benefit for me? If at all today's U squared is very high, the volatility will go up. Today's U squared is very low, the volatility will keep coming down. Right? So, if I bring in even the long-term volatility perspective, then probably some weightage will go to the long-term volatility, and that remaining weightage is split across these 30 kind of scenarios. So, those are the typical basic models to start with. Right? So, some of the drawbacks with this simple models, you are giving equal weightage. So, better give a changed weightage to each one of them, and if possible create a long-term weightage also, give some weightage to the long-term volatility also, and do the similar kind of a process. Now, this is where the most important things come into picture, wherein a small split up is coming up. While we have discussed that U squared is one mechanism to decide the volatility, right? U squared is one mechanism to decide the volatility. It has come out with another interesting aspect, that you find the volatility as of yesterday. So these are two components now. Volatility for today, break it down into volatility as of yesterday and yesterday's returns, U square. See, what is the change in the volatility between yesterday and today? The new returns corresponding to yesterday itself. That is what is the change in volatility between yesterday and today, nothing more than that. Right? The change in the volatility between yesterday and today is the yesterday's return square. So what it is saying is, you consider the volatility as of yesterday, give some weightage to the volatility until yesterday. Until yesterday means it's from yesterday till very old. Give some weightage to that, and give some weightage to the recent U square. So only one recent U square and the volatility as of yesterday. Build it as two separate pieces, probably in this. Volatility of 29th day and U squared of the 29th day. Volatility as of 29th day, because the volatility of 29th day is computed as U squared of 28 days. 28 and earlier. So that's the volatility on 29th day. Plus the returns on the 29th day, which is the difference between 29th day price and 28th day price, which is the log 29th day price by 28th day price. That's the returns which are extra for 29th day. That is U square. So for 30th day, I am saying some weightage is going for the 29th day volatility and also U squared. Some weightage for U squared, some weightage for this. I'll do the model, that becomes more easier for you. Okay, let's say I'm taking this, right? So now I'll take the U squareds from each one of them, right? So the U squared in each one of them is this much. Okay, so these are the U squareds for each. Now let's say for here, as of today, as of this date, right? If I want to find out, let's say the sigma or volatility previous, if I want to do for both of them, which is the sigma as of previous. So to start with, if I have only one day for me, forget about having 30 days data in this case. If I have it, good. But I am assuming that the stock got listed only on that day. I want to start off. So what I will say, the volatility as of this day, I can take it as the U squared of the previous day, because yesterday there was a change of that much. So if there is only one data for me, I'll start off saying that will be the volatility for today also. So I'm going with the volatility for this. This is sigma n minus 1 squared, right? Now from this day onwards, what I am doing is I am giving, to estimate the volatility for each of these days, I am giving some weightage to this, the volatility as of yesterday, and I am giving some weightage to this, which is the return squared that came as of yesterday, latest data, because this is based on up to here. This is based on this, right? So if I want for this is a new information. This is a new information. So if I have to do something for this day, what I'll say, I'm calling something as lambda, some weightage. How I find out the weightage, I'll come to that. I'll have some weightage called lambda for Dr. Reddy's and for HCL. I'm having some weightage. So let's assume for time being, I'm putting a 20% weightage here and I'm putting a 30% weightage here. I'll show what to do reality. So what we are saying is, I will give some weightage called lambda, right, to sigma n minus 1 squared. So if I give some weightage lambda to sigma n minus 1 squared plus the remaining portion of the weightage 1 minus lambda to the latest data ui squared. I can do that. So un minus 1 squared, even this is sigma n minus 1 squared. So only one previous value is sufficient at any point through this model. This is actually an iterative process, right? For tomorrow's volatility, I need only two inputs. Today's volatility, today's U square. I don't need anything previous because they are all taken care of in the today's volatility itself. Actually, from a statistician standpoint, these kind of processes, again, I don't want to confuse you, but these kind of processes are actually called as Markovian processes, Markovian models, where the today's value is dependent only on one period before, nothing more than that. I don't need historical data at all. So even with a small set of model, small set of data, I can do the whole modeling. So these are the two inputs I am taking. You got this? Okay. So I am giving some weightage to this. The same logic probably I can do in case of this. Whatever. I am just starting off with some dummy number. The model which we will use to typically do that calculation, we'll discuss on that. So I'll give some weightage to this. And I'll give 1 minus lambda weightage to the u squared. I'll give 1 minus lambda weightage to the u squared. So this is how the numbers are calculated. Now probably if you want for tomorrow, you can find out the volatility easily. You can find out the volatility easily now based on whatever is the lambda. So if you know that these are the lambdas, right? Now that today's volatility for HCl is this much, and the square of the returns is this much. You can do these two things, and you can find out the estimate of the volatility for tomorrow for this, even for this. So the only thing that is pending in this process is what are those weightages, right? If I know those weightages, everything else is clear for me, right? That deciding of the weightages is done through a process called maximum likelihood estimation process. I'll come to that, but just giving you a name for time being. Maximum likelihood estimation. In most of the regression examples, the way the estimation was done was on a principle called as ordinary least squares estimation method, OLS. We use the word OLS to a large extent, which is nothing but the error between the predicted value and the actual value. Minimize the error between the predicted value and the actual value is what we called as the OLS based, ordinary least squares. Minimize the square of the error. That is what we called as the OLS based estimation. In this case, we'll do the estimation through a process called maximum likelihood estimation. I'll come to that estimation process. How do we estimate these two things using the maximum likelihood estimation model? But just let's complete this part. So the exponential weighted moving average model, it generates through that process. You give some kind of a weightage called lambda to your previous volatility, yesterday's volatility, and you give 1 minus lambda weightage to the u squared of yesterday, because u squared of yesterday is like a new information for you. You are giving some weightage to that. And so now if you see here, this, you are giving a weightage to this, some weightage to this, and as of this, if you want, you are giving some weightage to this, you are giving some weightage to this. In turn, this one is giving some weightage to this and some weightage to this. So in turn, actually, in an iterative process, you are giving weightage even to the day 1 based on your day 200 also, right? Because so this is giving some weightage to this, whereas this is giving some weightage to this, which in turn is giving some weightage to this. So basically, every day volatility is dependent on all the days, correct? So current volatility, we are saying there are two factors that are coming in: the volatility until the previous period, yesterday, and the current period square returns. So depending on the what weights we are giving, what lambda we are giving, the impact, the predictions also will differ. So the determination of a lambda is a very important aspect in this entire process, which we will do using the maximum likelihood estimation process. So the advantage is, even with a very limited data set, I can go ahead with, as I said, only even if the stock is listed yesterday, I can start off with the model. Because it's a Markovian process model, it requires only one previous period of data, nothing more than that, to get started. Right? Probably if I have to compute the average for last 30 days, I minimum have to wait for 30 days and then only I can get started with the process. But with this, I don't need to wait at all. So even with a very limited set of data, I can start building my estimates. But the only thing is, as it keeps going on and on, the model gets evolving more and more effectively. Now, a modification to that EWMA model itself is called as the GARCH model. It's again the same as EWMA, but it has brought in the third dimension also, not just the two parameters. The two parameters it was talking of were the volatility until the previous period and the squared returns as of yesterday, as of previous period. Apart from that, it has also brought in something called as long-term volatility. So three things. Now it started saying there are three things. So there is some weightage that is going on to the volatility as of yesterday. Some weightage that is going on with respect to U squared as of yesterday. Some weightage that is going on to the long-term volatility. Some weightage that is going on to the long-term volatility. So if I assume alpha, beta, gamma are the weightages to each of these three, this model is typically called as your GARCH model. So the difference between a GARCH and a EWMA, EWMA does not take long term. So these could be the typical exam questions from this. The EWMA model does not consider the long term volatility at all. It considers only yesterday's variance and yesterday's squared returns. Whereas the GARCH, apart from those two, it even considers the average long term volatility level. One aspect. And the weightages alpha, beta plus gamma should be equal to 1. And even this estimation happens through the maximum likelihood method itself. We'll try out one or two of these things using the data itself, right? Then one more important factor. What is this GARCH PQ? PQ is, P is standing for number of lag terms of U squared. We are using only U n minus 1 squared. But if I use U n minus 1, n minus 2, n minus 3, not just yesterday's squared returns, but I need even the day before yesterday's squared returns also. When I say something like that, it becomes a GARCH 2 model. U squared, how many periods of U squared I am considering, it becomes in the GARCH that number would be put up in place of P. Similarly, sigma n minus 1 squared, how many periods I am taking? Yesterday's sigma n minus 1 squared, day before yesterday's, day before yesterday's. If I take all of them for today, see, it is saying today's volatility, if it is dependent on last 3 days volatility and last 3 days squared returns, then I'll write it as GARCH 3-3 model. Or today's volatility, last 2 days U squared and last 4 days volatility sigma squared, then I'll write it as GARCH 2-4 model. 2 means 2 days of U squared I require, 4 days of sigma n minus 4 days of sigma squared is what I require. But in this example, or the most common scenario is 1 period volatility, last 1 period volatility I require, last 1 period squared returns I require. The most common application is the last 1 period volatility and the last 1 period squared return. That is why we are calling it as GARCH 1-1 model. So we have to be, it's not a GARCH model, it's a GARCH 1-1 model, because GARCH is like a generalized. You can put any number and you can create so many models out of it, right? GARCH 1-1 is more generalized kind of stuff, more common kind of stuff, whereas a regular GARCH is, PQ is more generalized in terms of number of lagged periods of returns as well as the lagged periods of sigma n minus 1 squared. Now these three also are modeled through the same logic, maximum likelihood estimation procedure itself. The alpha, beta, gamma are determined through that maximum likelihood estimation procedure itself. Now, there are certain things from an exam standpoint, certain points to remember here. The alpha plus beta, which is the weightages you are giving to short term. Gamma is the weightage to long term volatility. The alpha plus beta are the weightages. You are giving one of them to the sigma n minus 1 squared and one of them to squared returns. So that alpha plus beta should be less than 1 so that gamma is positive. If it is greater than 1, gamma becomes negative. And if gamma becomes negative, you don't find a mean reverting nature in the data. Right? If alpha plus beta is less than 1, it even indicates the stability of our volatility. What does that mean? Even if it has gone up, it will come back to normal. Even if it has gone down, it will go back to normal. So there is some level of stability that you can depict in your data using this if the alpha plus beta comes less than 1. But if at all it comes greater than 1, ignore the GARCH model, go with the EWMA model itself. Instead of, so otherwise GARCH is more preferred to EWMA because it even takes into consideration the long-term volatility factor, long-term average volatility. So at least it shows some kind of a mean reverting behavior in them. Whereas when you are going with EWMA, the focus is more on only short-term volatilities. Correct? So EWMA is a special case of GARCH where long-term volatility does not exist, and probably the weightages are distributed only between alpha and beta. No gamma component existing. That is where the EWMA is a special case of the GARCH. And what we are also saying is if alpha is greater than alpha plus beta greater than 1, gamma will be negative weightages. And then it is better to use EWMA itself for a forecast purpose instead of GARCH. And some of the important things here, the persistence, which is actually given by your alpha plus beta layer. If alpha plus beta is very much less than 1, like 0.6, 0.7, once we calculate, we'll see in our example also. If alpha plus beta is very much less than 1, it means mean reverting is very fast. So even today, if the volatility is 30%, it can come back to 20% in no time. If alpha plus beta is very less than 1, 0.7, 0.6, 0.5, the more it is coming lesser than 1, it indicates that even though today the volatility is 40%, it may come back to its average, which is 20 or 25%, it may come back to its average very quicker. The same logic the other way. Even if it has gone down to 5%, within no time it may go back to 20%. But if the alpha plus beta is 0.97, 0.98 kind of stuff, though it is less than 1, though it is stable, but it takes too much of time to go back to average. Today, even if it is at 30, you can expect that it will take another few months to go back to its 20. That is what is the persistence factor coming up. So once we look at our numbers also, we should be able to do that kind of understanding. So that estimating of the parameters actually happen through a maximum likelihood estimation process. What does this maximum likelihood estimation process deal with? You choose the parameters alpha and beta or alpha, beta, gamma in such a way that they maximize the likelihood of observing the data in the sample. What does that mean for us in a simplistic standpoint is, using the data, whatever we have, you build a probability distribution equation corresponding to each and every observation. Now let's say if I assume that the returns, they follow a normal distribution. What you do is you identify the equation for the normal distribution. There is a general equation that is associated with the normal distribution. Probably for binomial distribution and all, we know some equation. For a binomial distribution, we say NCX into p power x into 1 minus p to the power n minus x. There are some formulas associated with each and every distribution. Similarly, for a normal distribution also, we have a formula called 1 by root 2 pi sigma into e to the power of minus half x minus mu by sigma whole square. The shape of that curve, we don't need to mug it up, we don't require it, we don't solve the question in the exam. But what I am saying is every, the bell-shaped curve is coming up because of that equation. Right? So what it says is, now every data is available with you. There is a sigma squared for every day. So you can find sigma for every day. And anyhow we have taken the x. So x minus mu we have taken as 0 in this example. So it is nothing but x squared. X squared is nothing but u squared in our example. U squared by sigma squared. We have taken the mu as 0 in this entire assumption. We have taken the mu as 0. So this is nothing but minus half x squared by sigma squared. X is nothing but each item squared, which is nothing but u squared. So I can take u squared by sigma squared. This is the probability that my current values for a first record, they go with the normal distribution. Like that I can do for all the 250 or how many records I have taken. I can fit a probability distribution to those values. So once I fit it, I maximize the value using some tool. So you will use linear programming kind of scenarios or probably solver kind of a tool. You use them to maximize that value and arrive at the parameters. So, okay, form an equation using the underlying probability distribution. So if I have to use a normal distribution, I'll use the equation like this: 1 by root 2 pi sigma into e power minus 1 by 2 x minus mu by sigma whole square. I'll use that kind of an equation. And you assign some initial weights. We have already done it, 0.2, 0.3, some initial weight we have given. And keep tweaking those parameters so that the overall likelihood is maximum and no more improvement in the likelihood comes out. Now probably I'll execute it using the tool. Probably you don't need to bother from an exam standpoint, but just from a practical standpoint. From an exam standpoint, probably this concept, if it is remembered, sufficient enough. Especially the game is with alpha plus beta. The majority of the game with respect to the exam, he gives one equation. And he talks about what is the persistence. Persistence is nothing but alpha plus beta. Or what is the mean reverting frequency? Can it revert much faster or very slow? Or he gives two such equations. He gives 3 weightages, one to long-term volatility, one to sigma n minus 1 squared. He directly gives the equation. He does not give the data for us. He gives the equations, and based on that he may ask us to find out what is the long-term volatility. Those kind of things he can very well come out with. Now, let's say if I have to do the same, the EWMA kind of a model, what I'll do is the likelihood. If I have to find out the likelihood, I'll apply that formula, 1 by root 2 pi sigma, whatever is there. I'll apply that formula here, 1 by root 2 pi, I am putting a sigma squared directly, which is because 2 pi and outside is the sigma. I am taking it inside the root itself, so I am directly taking the sigma squared. Root 2 pi sigma squared into e power minus half x squared by sigma square, x squared by sigma squared. X squared is nothing but u squared, x minus mu. Mu is 0, so I am taking x squared, which is the u squared, divided by sigma squared. So this is what we are calling as the likelihood function. Huh? I think it is fine. This is in the denominator. This is in the numerator. Where is another bracket coming up? Why? Hmm? No, that is fine. It takes as a numerator only. No, but I think this bracket is creating the problem. So I'll close this here. I'll close this here. And I don't need it here. Okay, I think it's the same. Okay, let me just give you the conceptual part of it. So these are the likelihoods for each of them. Now what I require is I maximize all the combination of all these values, which is nothing but the multiplication of all these I maximize. So what generally people do is the multiplication of all these is a very big number, right? Multiplication of all these is a very big number. So maximizing it is a very tedious task. So what people do is they take log likelihood. Instead of taking the likelihoods as it is, these are the likelihoods. I will not take the likelihood as it is. I hope the formula is correct. 1 by square root of root 2 pi sigma squared into e power minus half x squared by sigma squared. Looks fine. Okay. So I'll take the log likelihood instead of original likelihood, because see, logarithm I want to maximize a into b into c into d. It's as good as if I had taken a logarithm. I want to maximize the log a plus log b plus log c plus log d, because the multiplication, when I take a logarithm, it becomes addition. So the logarithm of each one of them, these are the logarithms of each one of them, right? The logarithms of each one of them, let's see. Yeah, no zeros, no errors anywhere, right? Okay, fair enough. The logarithms of each one of them is this much. So what does that mean to me? I want to maximize the summation. What is the sum of all the log likelihoods? This is the sum of all likelihood. Now what I want this number to be maximized. I want this number to be maximized. Maximum likelihood. Instead of likelihood, it's as good as, see, if I take the anti-log or e power of that, that is the original value, multiplication. So to make calculation easier, I'll take the log likelihood and I do the addition, maximizing the addition, not the multiplication. So what we generally do is, let's say a tool like Solver can help me in this process. What it generally does for me is, it determines that value. Okay, I want to maximize this value by changing this value, and I'll put a constraint here saying this value should lie between 0 and 1. Otherwise it can compute any kind of a value for me. I'll say that this value is less than or equal to 1, and this value is greater than or equal to 0. I'll put some small rules so that it does not give me the universal set of values. It gives me a value for this in between 0 and 1. So now let's assume that we get something better. So now it has said it is able to try maximizing 721. The maximum value has come out to 721.75, and the weightage it has given is 95.75 to the sigma n minus 1 square. 4.5% or 4.25% weightage has actually gone to the un minus 1 square. Now, probably if you check out, NSE daily publishes this volatility values. Right? I don't know if you have observed it. NSE daily publishes this volatility values. Or let me just take it out. But they do it not with a dynamic computation of lambda. They do it with a constant value of 94%. We got it as 95.75 using the maximum likelihood estimation now. NSE, whatever it publishes as a part of its report, you see, daily volatility file, as a part of that report, you see, the way they have computed the formula is they have given the 94% weightage to the sigma n minus 1 square and 6% weightage to un minus 1 square. If you see this is the u. They have given a 60%, 30% weightage to the un minus 1 square, and this is nothing but the previous day's close price. So which is they are giving more and more weightage. You see here the current day volatility they are taking through this, whereas the previous day's volatility they are taking. So the D is actually this. Yeah, these are these, not the D column. So C they have taken it as log A by B, which is nothing but the, the log returns, the continuously compounded returns. This is what they called as C. And D they took it as previous day's volatility. So the same logic which we have done, but instead of dynamically computing for all the securities, they do it on a static basis. Even that will create a volatility difference, because now if NSE predicts the volatility for Dr. Reddy's, they predicted based on 94% for volatility of yesterday and 6% for the yesterday's date, yesterday's change in price U square. But when I have to predict it, the appropriate number is 95.75 and 4.25. So there is a 1.75% difference between the static model and the dynamic model. If at all I have to play with options, this number will give me a very big hold compared to the existing number. The same logic you can repeat with a GARCH model. Now, just for quickness, if we have to see the GARCH model also, even if the GARCH model is going to make any kind of a difference to our analysis, because even the NSE uses EWMA model itself, right? Just like the way we have done it. Now, in case of GARCH, what difference comes out? The volatility previous is remaining the same. U squared is that. the volatility previous. Now I'll bring out alpha, beta. These two parameters are required, and probably gamma, and gamma into VL, because VL also we don't know. So gamma into VL, there is another thing I call as omega. Just a multiplication of gamma into VL. I'll treat it as omega. So if I give, I'll actually estimate these three. I'll estimate omega into omega, which is gamma into VL. I'll not estimate gamma, because gamma can be derived once I know alpha and beta. 1 minus of alpha plus beta is gamma. So I don't want to estimate gamma separately. But I want gamma into VL, which is nothing but omega, which will help me to decide what is the long-term volatility for this security. Is there any impact of long-term volatility for this security? So what will happen to my latest, this modified equation, the same log likelihood, everything will remain the same. So what will happen for the first day, I will take the volatility like this itself, which is the previous day's U square. But from the next day onwards, I'll take it as three parts. The gamma times long-term volatility, this number, gamma times long-term volatility, plus let's say some alpha times this. So alpha is the weightage I am giving to sigma n minus 1 square, plus beta times u n minus 1 or u I square. This one, correct? So this is what I am giving. The same logic. Now you keep continuing. Probably it's better that we give some numbers, 0.4, 0.6, 0.5, and probably some rough numbers is what I'm starting off with, so that it won't show zeros and it won't create kind of nuisance for me. So the values the volatilities I'm getting through these numbers. Now the same likelihood function I can apply, because this is also a normal distribution. I'll apply the likelihood function 1 by square root of 2 pi sigma squared into e power minus 0.5 x squared by sigma squared. X squared is nothing but u squared by sigma squared. Correct? So this is my likelihood function. This is my likelihood. I have to maximize the multiplication of all these as good as multiply the logarithm, maximize the summation of the logarithm of all these. So what is the summation of the logarithm of all these? I'll find out that the summation of the logarithm of all these is this much. I want to maximize this value by properly estimating these values, right? So what I can do, again here I'll set up, maximize this value by changing this, comma, this, comma, this. These three you play around, and we can also set some kind of rules. Omega can become negative for us if alpha plus beta is greater than 1. Omega will become negative, right? So I think this is sufficient to start with. So let's assume the numbers. Let's see what it can give. So I'm taking these two kind of criteria itself, and let's solve it. Okay, otherwise to start with, I think there could be some problem with the Excel spreadsheet kind of solution here. But probably let's go with an assumption. Let's go with an assumption that I'll even set omega also to be greater than or equal to 0 itself. I mean that's again depends on how the spreadsheet is treating each one of them. But just from a model standpoint, I want to tell you what is typically going on. So I'll keep let's say the omega is positive, right? Just adding up one more rule, and let's see if it works out now. In this case, it was able to come up with kind of an allocation. Probably again, this is the kind of limitation which the system is also having, right? Depending on the time it takes to execute and all, it comes out. But otherwise, so in this model, it is saying the maximum weightage it is giving to beta itself. Beta is nothing but u squared. So, I mean, what could happen is generally you will have different weightages existing to all three of them, right? What you will see is the alpha plus beta will have a relatively very high weightage, very close to that 95, 94 mark. And the gamma will be having a much lesser, probably 5% kind of weightages, which means long-term weightage is something like that. So, in the question, sometimes what he gives is the omega into or probably gamma into VL is the long term weightage. So he gives an example saying that the variance of the portfolio is equal to, let's say, 0.0003 plus 0.6 times un minus 1 squared plus 0.35 times sigma n minus 1 squared. Let's say I give one question saying sigma squared is equal to 0.0003 plus 0.6 times the un minus 1 squared plus 0.35 times. This is the most common question that may come up. 0.35 times sigma n minus 1 squared. Based on this, find out the long-term volatility. So now we know, because the weightage per alpha and beta is 0.95, 0.6, 0.35. 0.95 is the alpha plus beta. So gamma weightage is 0.05, right? Gamma weightage is 0.05. But what is this 0.0003? It is gamma times VL. 0.0003 is gamma times VL, and gamma we know as 0.05. So VL is nothing but 0.0003 divided by 0.05. This is your long-term volatility. And if you are asked about the standard deviation, long-term standard deviation, I can take the square root of that and say probably 7.7% is the long-term standard deviation in this case. And another question that can crop around is this what is the persistence level? 0.95, right? Is this mean reverting or non-mean reverting? Because alpha plus beta is greater than 1, it's not mean reverting at all. Only if the alpha plus beta is less than 1, it comes back to the long-term volatility, right? And what is that long-term volatility level? 7.7%. So today it may be more than 7.7 or it may be less than 7.7, but it will come back to 7.7. That's the average level of volatility that keeps fluctuating over the period. So typically the GARCH models and all, they are very good at predicting, or they are very good performers for predicting the volatility clustering, especially like, again, if the volatility is in some trends, at least for some periods, it's growing, falling, some kind of trends that are there, they have a good predictability. So like today high volatility followed by another high volatilities kind of stuff. Suddenly there is a drop, very high, suddenly there is a drop. They have some kind of limitations in terms of predictions at those kind of layers. And if, see, if one thing, if the GARCH models and all are very good, there should be a lot of independence established associated with the squared returns to the variance kind of parameter, because they should not be correlated with each other. So that if that exists, so if I find out the squared returns to the variance, find out the correlation between them. If it is almost negligible across time, if it is almost negligible with a time lag, if I take, if it is almost negligible, then it means my GARCH model has done a much better prediction itself. And in most of the cases today, GARCH and EWMA are the most common methods. Even if you see NSE has published only an EWMA based volatility forecast. So today GARCH and EWMA are more common kind of mechanisms that are used for predicting your volatilities across the periods. So that gives us, even for our from our options pricing standpoint and all, also these models become more and more comfortable. And finally in this chapter, just like the way we have forecasted volatilities, which are nothing but variances, we can forecast covariances, right? Because just like, okay, add up the variances, add up the u squareds of the last some periods. When I say covariance, instead of u squared, add up uy. Add up uy, because covariance is taking two variables at a time. Instead of adding up the u squared, you add up uv. You multiply uv for each of the days. Instead of u squared, you do a uv and do a average of that. Again, EWMA, the same logic. Give more weightage. So you take the first day's uv. Instead of u squared, you take the first day's uv as the covariance. From the second day onwards, you give some lambda weightage to the previous day's covariance, and 1 minus lambda weightage to the recent uv. Just the same replication. Whatever you have done with respect to u squared, you do the same process with uv, right? And correlation is nothing but covariance divided by the individual standard deviation. Individual standard deviations you are already doing through the volatility prediction. For each of them you are doing a volatility prediction separately. So you get the individual standard deviations very well. Covariance you can get in the same process you are doing the variance. Instead of u squared, you do an uv. That's it. Finally, you are getting your u squared when volatility forecast per x as well as per y. Take the square roots, you will get the standard deviations for both of them. Using them, you will find out the correlation. But of course, the process is very tedious, computation heavy. So you have to be slightly careful in the calculations that are done at each of the layers. But yes, one more thing that is worth remembering again from an exam standpoint is maintain consistency. If you have used EWMA for variance forecasts, use EWMA only for covariance also. GARCH for variance, use GARCH for covariance also. Don't vary the models between the variance and the covariance computation. And for all variances, use the same model. If you are going with EWMA, go with the same. If you are using GARCH, you are using the same. So the consistency should be the same across all the models. So only then the correlation forecast comes more and more appropriate. And even that will be used very heavily in your portfolio management model. So from that standpoint, in very heavy uses in risk management and portfolio management, and that too options where you use them for hedging purpose. In all these cases, doing these kind of calculations and all will be practically very helpful, right?